All right, new topic in this class. We are now going to start talking about applications of integration. So what we do in chapter 6 is we take all the knowledge that we gained in chapter 5, where we learned how to calculate all these different integrals, and we learn some things we can do with this newfound knowledge. So chapter 6, last thing we do in this class, it's all different applications of what we learned in chapter 5. And the first one really isn't all that interesting. In fact, we kind of just learned the first one so that we can do what we'll end up learning in 6.2 and 6.3. So it's more just a foundational section. And what you'll see is the ideas of 6.1 really just follow pretty naturally from this idea that we already have that the definite integral is just the area underneath the curve. So the questions in 6.1 where we learn a little bit more about area might look different than the questions that you've seen before about the area underneath the curve, but I want to make the argument that it's really the same. So a typical 6.1 question might ask you to find the area that's bounded by these two curves, f of x and g of x. Right, so how much area is there in between the green and the blue, like in this little weird shape right here? And generally you would have an equation here and you'd have an equation here and you'd actually figure it out. In this video, I don't want to actually figure anything out. I just want to talk about the intuition for what you'll end up doing. And essentially all you'll end up doing is finding out how much area there is underneath f of x and then subtracting how much area there is underneath g of x. And you could talk yourself into it just doing the rectangle argument, which is really the argument you'll end up doing a lot in calculus. It's hard to picture the infinite case where we have infinitely many rectangles that make up the area underneath the given curve. But if you just think about a single rectangle that won't be infinitely skinny, just to sort of get the idea of what's going on. If I talk about the area underneath the curve f of x, a typical rectangle might look like this, right? I don't know if I'm using left endpoints or right endpoints. I made the rectangle small enough that you can't really see. But if I were calculating the definite integral between some bounds for this function f of x, I would have to figure out the area of a bunch of different rectangles that look like this. And if I did the same thing for g of x, a rectangle might, instead of looking like that, look more like this, because it's just the area below the blue curve. And note that if you take the green rectangle, which goes all the way from here down to the bottom, and you subtract the blue rectangle, what you're left with is just this rectangle that kind of spans the area in between the two curves. Essentially, all that I'm saying here is to find the area bounded by two different curves. All you're going to do is find the area beneath the top curve and then subtract the area beneath the bottom curve. And you're like, whoa, that's going to get really weird. What about sections down here where the area is negative? Turns out that works out perfect. What you'd want if you're figuring out the area in between the two curves is a rectangle that goes all the way from green here down to blue, right? If we were trying to figure out the area in between the two curves. Well, if I figured out the area underneath the green curve, my rectangle would go from here to the x-axis. And then if I figured out the area underneath the blue curve, I'd get a negative number, because remember, area underneath the x-axis counts as negative area. So if this area is, I don't know, 5, and this area is -2, 5 minus -2 gives me 7, which would be the total area of this hypothetical rectangle here. The point is just, it doesn't matter where your curves are, if they're above or below the x-axis, everything works out fine. All you got to do to find the area in between two curves is subtract the definite integral of the bottom one from the definite integral of the top one. So to make things a little bit more concrete, this area starts right here where these two curves intersect. Right? This is one of the 2 points where f of x equals g of x, where their heights are identical. We're going to refer to this point right here as a. And this is the other point where these two curves intersect, where the heights of the two functions are equal, and we'll refer to that as b. If we want the area that's depicted here that's bounded by the blue and green curves, all we would have to do is calculate the definite integral from a to b, these two different points of intersection, of the top curve f of x minus the bottom curve g of x. And in the next example, where we actually end up doing these, you'll have an equation for f of x and you'll have an equation for g of x. And when you're dealing with definite integrals, sums or differences of two different functions work out really well, because essentially it just changes one question into two different questions, because you can take the antiderivative of each function individually. So what you'll see is there isn't that much new stuff in what we've talked about so far in 6.1. Before I end this video, I want to talk about one more generic case, one more general case where I don't give you the actual functions and I just kind of talk about the theory of what we'll be doing, because I think it'll help to have this theory when we go into the next video where we actually do examples. So consider this picture right here. And what if I asked you how much area is there bounded by these two different curves? You might think that we can do it exact same as we did before, right? You can think about a general rectangle like this one right here. The curve up on top is the blue one. The curve down on the bottom is the green one. So to figure out the area, I would just find the points of intersection, and then I would integrate between those 2 points of intersection, and I'd take the blue one minus the green one. But that's not going to work. And the reason that's not going to work is because the points of intersection are right here and right here. So I would only be integrating from this point to this point. And if I tried to integrate to the left of this point, look what a rectangle would look like. It wouldn't go from blue to green. It would go from blue to blue. So it wouldn't make sense to take the area underneath the blue curve and subtract the area underneath the green curve, because the green curve doesn't even come into play with this rectangle right here. So clearly something's going wrong. And if you look at it long enough, you'll figure out that what's going wrong is g here is not a function. It's not a function of x. It doesn't pass the vertical line test. That's why I didn't write it as g of x, and I didn't write this as f of x. So the problem is we won't be able to solve it the same way we did over here. The other thing that you'll want to learn how to do in this section is recognize that when you're in a case like this, we can integrate with respect to y as opposed to with respect to x. What am I talking about? Let me show you. The 2 points of intersection of these 2 curves occur right here and right here. And we're used to thinking about the x values at which these 2 points occur. But for this example, we're not going to think about the x values at which these 2 points occur. We're instead going to think about the y values at which these 2 points occur. So this will be y equals a, and this will be y equals b. So instead of integrating from x equals a to x equals b like I did here, where this a represents how far left and right I am, and this b represents how far left and right I am, I'm going to integrate with respect to y. Instead of having a dx right here at the end, I'm going to have a dy. I'm still going to integrate from a to b, but my variable of integration will now be a y. How's that going to work? If your functions are written in terms of x, how is your variable of integration going to be a y? Well, the short answer is it's not going to be. I'm not going to think about these as functions of x. I can't think about these as functions of x because g is not a function of x because it does not pass the vertical line test. What I'm instead going to do is think about these as functions of y. And of course, I'll show you how to do that in the next video with a concrete example. But the basic idea is when you think about something as a function of x, like this thing g is a function of x, what the function does, what the machine does, is it gives you the y value for any given x value. So you put the x value in and the y value comes out. If you have a function of y, it's just the other way around. It gives you the x value for any given y value. So instead of putting in a point like this and getting this to come out, I'm going to put in a point like this and get this to come out. I'm going to put in a y value and get an x value to come out. So instead of g of x and f of x telling me the respective heights like I have here, g of y and f of y are going to tell me the respective, lengths, the respective x values. I don't know what term you want to use to signify that, but hopefully it makes sense. When I think about a typical rectangle, it's not going to be a vertical rectangle like I drew here. It's going to be a horizontal rectangle. So the area beneath, in big old air quotes, f of y actually shows up to the left on the graph. If I took the integral from a to b of f of y, I'd be talking about how much area there is out to the left of this curve in green. Similarly, if I took the integral from a to b of g of y, I'd be talking about how much area there is to the left of this blue curve. Maybe this picture helps, or maybe it just makes it hard for you to look at. The integral from a to b of g of y would be this area shaded in blue. And the integral from a to b of f of y would be this area shaded in green. And if I took the area shaded in green and subtracted the area shaded in blue, what I'd have left is this area bounded by these two different curves, which is exactly what I want. What I'm saying is the same trick we did up here, where to find the area bounded two curves, I just have to take the definite integral of the top one and subtract the definite integral of the bottom one. The same thing works here. I can also take the area to the left of the curve with the larger x values over that region and subtract the area to the left of the curve with the smaller x values over that region. We do top minus bottom, we do right minus left, and we'll get some concrete examples of both in the next video.